For our fifth lesson of our Introduction to Calculus here, we are going to be looking at something called the limiting process. We are now getting into more of the need for calculus, as we've been dealing with an average rate of change, also known as the gradient, also known as the slope of different functions. And we started out by looking at when we took the slope or the average rate of change between 2 points on a line. We saw that on a graph like that, the slope is always constant. So anytime we had a linear function like this, we could take any 2 points on the graph and throw them into our slope formula in order to get the slope or the average rate of change between those 2 points. And we took a look at when it's a line, it doesn't matter what 2 points you use, you'll always get the same rate of change simply because it's linear, so slope is constant when you're dealing with a line. But in the last lesson that we dealt with, in lesson 4, we saw that what if it's not a line, what if it's a curve? And so when we have a nonlinear function, something that's curved, let me go back to that one from our last lesson, right? We could see that my slope is always changing. It's never constant. So I'd have a slope at this point. That would be different than my slope at this point right here. That would be different than my slope at this point right here. I'll draw a couple just so we can see it. But you can see I have a slope that runs right through that point. That would be different than if I had a slope through that point, right? All those would be different. I have a slope running through that point right there that looks like this. So I have these constantly changing slopes. So every point on this graph has a different slope than all the other points. And so if I were to take this is what we did between all of these guys, but if I took the average rate of change between those 2 points, I get this slope. The average rate of change between those points, I'll get a different slope. Average rate of change between those points, I get a different slope. So depending on which points I pick, I'm getting a different slope between those 2 points. And so I'm getting this ever-changing slope as I move myself through this curve. And so what we're looking at today is, what if instead of an average rate of change between 2 points, we wanted an instant rate of change at only 1 point? Well, this is where we run into a bit of an issue with the slope formula, because in slope formula, remember the one that looks like this, in order for that formula to work, I need 2 different y values and 2 different x values in order to use that formula. So how can I get an instant rate of change at only 1 point when my slope formula requires 2 points? And so this is where we get into more of the need for calculus, is getting an instant rate of change. We're going to be looking at, in today's lesson, in the 5th lesson, something called the limiting process, which is the idea of, what if I wanted the slope at this point right here, just that 1 point? Well, I could start by getting the average rate of change between those 2 points, and that would give me something kind of close to this slope, but it's still not just the slope at that 1 point, right? It's the average slope between 2 points. Well, what if I moved closer and found the average rate of change between those 2 points? Or what if I moved even closer and found the average rate of change between those 2 points? We're going to see the closer I move towards my target, towards the point that I really want, we're going to get closer and closer and closer to the actual slope at that point. So this is what we call the limiting process. It starts with just taking 2 points and finding their slope. And then as we keep doing more and more, we zoom in on the approach of getting closer and closer to just 1 point, the one that I want. And so we're going to see that as I use those 2 points, and then those 2 points, and then those 2 points, and we're going to get closer and closer, and we're going to get so close to that point right there, the slope at that point is going to become obvious to us. And so we are going to zoom in on a single point. And so it's just so we can use the slope formula, we have to start with 2 points, but then we're going to use 2 closer points, 2 closer points, and we're going to get closer and closer and closer to our 1 point that we really want. And so that's the idea behind all this. Okay, so here's the function we're going to be using for our first example, 3x squared. And so we're going to use what we call the limiting process in order to get a rate of change, also known as a gradient, also known as a slope, at a single point on the graph. So, as you were just seeing on the last graph, I'm going to be using 2 points, but I'm going to be zooming in on or getting closer and closer and closer to the point that I want. The distance between my 2 points, so we're going to take a look at this graph. We know if it's 3x squared, right, it's going to be a parabola. So if I were to graph this guy, I know it's going to look something like this. And just a rough sketch here. And so we're going to be looking for the instant rate of change at the point where x equals 2, which is going to be somewhere right about there. Right? And so I can see there's a slope right there that looks just like this, and I want to know what the slope of that little line would be at just that single point. And so we're going to start with 2 different points, and the distance between those points is represented by h. If you remember what we talked about in the last problem, where we said I'm going to pick 2 points because I need 2 points in order to use the slope formula. So I'm going to start with 2 points, and then I'm going to zoom in on my target, which for this problem is 2. And so, like, let's just say I wanted to find the slope from where x is 2 to where x is 3, right? Between those 2 points right there. And so I want to get the slope between those 2 points. And then if I got a little closer, maybe from 2 to 2.5, right? And I'm going to get the slope between those 2 points, and that's going to get me even closer to my target. And then maybe from 2 to 2.1 and get even closer to my target. And so we're going to be taking multiple slopes, but we're going to be getting closer and closer and closer to the one that I actually want, which is where x equals 2. And so we're going to zoom in on that point. So keep in mind what h represents here. H represents the distance between the 2 points that I'm using. So for example, if I wanted the slope between where x is 2 and where x is 3, that would make h 1, right? Because that would take me from 2 to 3, and that would make h 1. That's the distance between this point and this point. Or if I went from 2 to 2.5, that would make h 0.5, right? Because I would be going from 2 to 2.5, and that would make h 5. So h represents the distance between my points. And I want h to get smaller and smaller and smaller so that I get closer and closer to that guy right there. And so that's the idea. But here's the issue is I don't want to do a slope from 2 to 3 and then 2 to 2.5 and then 2 to 2.1. That would be a lot of slope work. So what we're going to do is we're going to develop an expression that we can use for all those points at once. And so that's why we're using from 2 to 2 plus whatever, and develop an expression that we can use instead of having to use my slope formula again and again and again, because that would take forever. So we're using an expression that will go into our slope formula and creates a scenario for us that'll make it a lot easier and a lot quicker to zoom in on our target of where x equals 2. And so because it's 2, we're going to use 2 as my first x, and then 2 plus h as my other x in order to develop this expression. Keep in mind, with our slope formula, remember that it is our y minus y over x minus x, right? That's the slope formula, or the gradient formula that we're using here. So what are the y's and what are the x's? We just said that this is my first x and this is my second x. So as far as the bottom goes, I'm going to do my second x minus my first x. That's what always goes on bottom. On top I need y minus y. Well, how do we get a y value to go with that x value? Right? Well, we plug this x into the function in order to get a y value. So this x is going to get plugged in, so we're going to call that f of 2 plus h, right? Because we're going to plug in 2 plus h into the function in order to get a y coordinate. Same with this guy. In order to get a y value to go with him, I need to plug 2 into the original function in order to get a y value that goes with him. So we're still doing y minus y over x minus x. You can see on the bottom, this will always simplify to just be h, because I'm going to have a 2 minus 2 that will cancel, and that will always happen, and I'm going to be left with just h. On top, however, this is where kind of the work comes in, because I have to plug in 2 plus h into this in order to get a y coordinate. Then I have to plug 2 into this in order to get another y coordinate. So I'm going to do a little side work here, and I'm going to start by plugging in 2 plus h in there for x. So we have 3, 2 plus h squared. And if I simplify all that, so if I did 2 plus h times 2 plus h, and I FOILed that, I'm going to get 4 plus 4h plus h squared. All right, if I were to expand this and FOIL it, and then I'll distribute the 3, and that's going to give me 12 plus 12h plus 3h squared. And so when I plug in 2 plus h into that function, this is what I get out of that. So this is the y coordinate for that x coordinate. This guy's going to be a little easier because it's just a number. So when I plug in 2 into the function, I got 4 times 3 is 12. Remember what we talked about right here? That minus that would just be h. And so after a little cleanup here, you can see that 12 minus 12 would cancel. So all I'm going to get is this little interior right here. So 12h plus 3h squared over h. And now I have one more step. Since h divides into everything, I can divide out the h and get my expression, which is just 12 plus 3h. So remember what we just developed right now is we just developed an expression for slope that we can use, and h represents the difference between the 2 points that I'm going to pick. As we zoom in on where x equals 2, so we're going to make a table here so that you can see as we get closer and closer and closer to that target point where x equals 2, I'm going to get a real good idea of what the slope is as I get closer to that point. Really important that you understand that h, as we talked about up above, represents the distance between my points. So from here to here, we said h would be 1. From here to here, h was 0.5, and so I want h to get smaller and smaller and smaller. In other words, as h approaches 0, I get closer to my target point. So we're going to set up a little table here. We got our h's on the left. That's what we'll be plugging in to this expression. So we have the results on the right. And so let's just say we wanted the slope from 2 to 3, right? What would that make h? Right? So h would be 1 in that case. And so if I were to plug in a 1 into this, you could see 12 plus 3 would be 15. If I went from 2 to 2.5, that would make h, as we talked about right here, that would make h 0.5. And so if I did 3 times a half, I get 1.5 plus 12. So there's another slope. So remember what this represents. So from 2 to 3, that would make h 1, and I would have a slope or an average rate of change between those points of 15. And if I went from 2 to 2.5, that would make h 0.5, and that would give me a slope between those 2 points of 13.5. So I'm getting all these slopes right here, and you're going to see as h gets smaller, and I get closer and closer to my target, it's going to become obvious what our slope at that point really is. So we're going to make h even smaller just to make it obvious. So it's going to be 0.1. We're going to do 0.01, and then we're going to get super close to our target by doing numbers like this. And so let's punch in a few of those so we can see those values. So if I plugged in the 0.1, so 12 plus 3 times 0.1, I'm going to get this. If I plug in 0.01, I get this. As I plug in an even smaller value for h. So you can see what's happening on the results here. As h gets smaller and smaller and smaller, or in other words, as h approaches 0, what do the results become? And you can see by these numbers, I am getting closer and closer to 12 the smaller h gets. So we had 12.3, 12.03, and you can see the smaller I make my h value, the closer I get to 12, which tells me that as h approaches 0, I'm getting a slope of 12, which must mean that the instant rate of change, or the slope, at that one point is 12. So if I were to draw like a little tangent line that hits that point where x is 2, the slope of that tangent line would be 12. And that's what we're really seeing out of this. So we just found an instant rate of change at a single point by using this limiting process. And we're getting 12 as our instant rate of change. Keep in mind, here's sort of the obvious that you guys are going to notice as we do these. If h is approaching 0, look at our expression. Well, if h is basically becoming 0, what am I going to be left with? Right? So 12, we're going to see by understanding that if I just put in a 0 for h, I see my instant rate of change at a single point is 12. So we're going to do one more here. I'm going to go a little faster through the second one. New expression. I now want to know where the instant rate of change where x equals 1 is. So because it's x equals 1, I'm going to use 1 to 1 plus h, where h is getting smaller and smaller and smaller, to get my instant rate of change. So here's sort of the quick version that you'll do in homework today. If x equals 1, then I want to use 1 to 1 plus something as my x's. So I'm going to have to plug in those x's in order to get y values, because all this is coming back to our slope formula. Right, so I'm doing y minus y over x minus x. This guy and this guy will always cancel, and I will always be left with just an h on bottom. On top, I need to plug in 1 plus h for x in order to get a y coordinate to go here. So if I did 1 plus h squared plus 2, I'm going to get the y coordinate that goes right there. So if I expand out my 1 plus h, I'm going to get 1 plus 2h plus h squared. A little plus 2 at the end. So combine like terms, and I'll put it in order, h squared plus 2h plus 3 is that y coordinate. Then I'm going to subtract what I get when I plug in a 1. So if I did 1 squared plus 2, I get 3. So there's my other y value. A couple things that will always happen if you do this right. I'm going to be left with my constants will cancel, and I'll have an expression that only has h in it. So that I can then divide out the h from my two terms. And there's my expression. So as we set up a table to find the instant rate of change as h approaches 0. Remember, we already know what's going to happen here. If h is becoming 0, what would I be left with? Just 2. So I already can tell by this expression that my instant rate of change, or you could say the slope of that curve at this single point, is going to have a slope of 2. But we're showing a table to represent that so that we can show, oops, let me do this. So we're plugging in h. The result was h plus 2. So we're going to use tiny numbers because remember h is approaching 0. So we would go for 0.1. We'll show a couple obvious ones here just to make it clear. But if I put 0.1 right there, right, I'm going to get 0.1 plus 2. And then 2 plus that. And you can see as h approaches 0, my slope approaches 2. And so I can see that my slope as h approaches 0 is 2. So we just found an instant rate of change at a single point instead of an average rate of change between 2 points. And so that's what this guy was all about.